any structure we come across this phenomena when there is an abrupt change in the structural arrangement, or what we say when there is a structural discontinuity. Say for example, in our ships we will find, let me draw the profile and I will try to clarify. I am drawing the old type of profile. So, you have the main deck here, and then you usually have a forecastle. Okay. Sometimes you may have some increased portion here also known as the poop. And if you see it from outside, what we do, that we have a bulwark goes like this, so this plating which is there goes like this, and actually the deck is something like this. So, there is a discontinuity here. Now, if we wanted to give the bulwark, we could have finished it here, put a ladder sort of a thing here, and then start the bulwark and then finish it. But we don't do that, and we are trying to give it. Now, there must be some reason why we are not doing that. Can you tell me what are the reasons?
So first of all, a continuous member will take the which is for this break, that load. Part of that
load comes later on. Number one, what we do, that this is the part which can be seen outside. It should look pretty. And if you have a discontinuous thing, it doesn't give a very appealing look. And therefore, if you have some smooth covering like this, it gives a good look. So, look wise it is good, smooth. And then comes the structural part, that all these discontinuities are concealed. Now, the actual thing comes that this vessel, when it flexes, there is some sort of a additional stress comes here. So, if we continue in this fashion, then the stresses will come here. Okay. And for that, let me try to just take a simple example, that you have a plate, let us say a rectangular plate, and we give a small hole here, and if we subject this to say uniform tension, then what type of stress variation will be there? If you take a section somewhere here, stress variation is like this. You take a section here, this is the whole part, there is no plate. Obviously, when the material is not there, the stress will not be there. But how the stress goes here?
Stress will be maximum on the end.
Yeah, yeah.
No, on top.
No. You take a section somewhere here. Section is complete. Sorry, it will be something like that. Okay, it will be something like this. Now, what makes it to go like that? Here there is a discontinuity which is coming. As a layman, we can say that the amount of stress which was supposed to be taken by this part here is not there, and who is going to take it? It is the neighborhood who will have to bear the brunt, and that's what happens. Now, many people try to explain it like this, that you consider stress is flowing like a fluid. So, if we are talking about a plate like this, the uniform stress which we are saying is going like this, and then suddenly the material is not there. So, this stress line will go from here to here. Okay. But this stress line which was supposed to go straight does not find any material, and therefore it bends and goes like this. This line goes like that. What happens to this place? What happens here? This also bends a little. Now you see what happens. Because this material is not there, all these stress contours are trying to reach there, but does not find anything. It takes the shortest path and goes like that. And as the concentration starts, so it gets deflected a little bit, and then it finds that yes, it can go like that. So now if you just try to plot it, that gives you this variation. Okay. And you will find that the smaller the hole, larger this will be. I am not going into the mathematics of it, but if you consider this part here, let us say that this is sigma 0, and I want to plot this as sigma across this, and if I say that this distance from the center is some r, and I take that half diameter is a, then I can write it is derived that sigma is equal to sigma 0 by 2 plus a square by r square Okay. So, this is the stress value which you get. Now, what is this value here? This is the stress value at sigma at r is equal to a, and if you substitute that value, okay. So, this part has been mathematically derived from theory of elasticity. I am not going into the details how it has been derived and so on and so forth, but knowing this fact that as soon as you make a hole here, the stress which you will get at this place will be of this order. So, the discontinuity is giving me a value like this. Now, if suppose I like to find out, say at r is equal to 2a, what will be the sigma value? Sigma value will be of the order of 1.218, I think. Okay. At r is equal to 4a, you say. This will be of the order of 1.032. And r is equal to say 10a. How much it is? This we should be in a position to calculate. .0016. Okay. So you see how it changes. If now I try to plot it, what is the value I have taken? This is 3, 1a, 2a, 2 is 1.2, 3, 4 is okay. So this let us say is 0016, this value is 032, this value is 1.218, this is 3. So you see in the vicinity, this is 200% more, this is 22% more, this is 3% more, and of course this is only 0.16% more here, just because some material is not available. Some increase will be there because they have to share it. This material is missing, but you see who shares the maximum is in this vicinity. So the concentration of the stresses is around this area. Okay. Now when we come to the ship's part, obviously when you have a deck, we say that you have the deck here and you have an hatch opening. We round it up, we don't leave it just like that. It will be easier for us to cut it straight, and then you have the flanges also straight there, but we round it up basically to make it smooth like this. Okay, and then even after that, what we find that the stress value will be of this order. So stress here will be of that order, and to take care of that in this vicinity, it's not only here. What you can see is that as you go a little away also the stress percentage is quite high. Okay. So what we do, we try to increase this part. I think it is something like this, and you have a plate on this side, which normally we try to give it in this shape, an octagonal diamond shape we say.
Is it a doubler plate?
Diamond plate in two ways. Either you have a doubler or you have a thicker plate replacing this thin plate here. Okay. Now this will try to give you that what should be the thickness of this additional doubler plate. But these days we are not going for the doubler plate, just because if you are having two plates welding, there is every likelihood that some gap will be there, and there will be a passage for the oxygen to get inside, the water will go there, the moisture will be there, and there will be a galvanic action between the two plates there, quite likely. Okay. And therefore inside you cannot protect it, so you just simply remove this part and change it with a thicker plate at this edge here. So all these areas are strengthened to take this additional stress value. The same is the reason when we are trying to do this. Now this particular ship will be under bending, so what will happen? This particular plate will be under stress, tension, compression, whatever it is, and this part of the shear strake we would like to strengthen it. That is the reason why this plate is not given in this fashion, because this will also be subjected to that, and therefore we try to give a extended part in a smooth fashion here. Okay. So this is the reason why in these places we have a plate like that. You see the practical aspect of it, and also you try to concentrate something on the aesthetic part of it, and matching the two, we try to come out with some solution. Okay. Now there are other things that here itself, let me say that near the engine room you may have many holes either below the water line for sea intake or slightly above the water line for the discharge. So these are all circular holes, maybe of 2-inch diameter or 4-inch diameter, from where you are sucking in the water and you are also throwing away the water after treatment, etc. Or it may be just for the cooling purpose, for the heat exchanger or some such thing. You take the sea intake and then you throw it out. Continuous process. Now these holes which we make will be subjected to this stress concentration, and therefore for the compensation of this we try to strengthen them by putting a ring sort of a thing. We can say that the pipe which is welded there itself will act as a flange, but again we cannot 100% be sure on that side. So we put the pipe from inside, but from outside also we try to put a ring sort of a thing. So this part is different. Okay. The same thing on the deck, we have the manholes, and we try to put this radius there, and this radius we try to put that, one can see that more will be the radius here. Again, from elasticity you will find that this stress which is here will get slightly tapered down. Okay. So if you are having a smaller hole, more concentration will be there. If you have a bigger hole, then the concentration is reduced. Now this phenomena I will try to explain you. You must have read it that during the early 90s many bulk carriers were lost in the sea, I think according to the recorded these things, some about 56 bulk carriers or 56 ships, in which majority of them were bulkers, between I think 91 and 93 were lost. And when some sort of investigation was carried out, they found that the average age of the bulkers were something between 12 to 15 years. Okay. There were about 20% vessels which were beyond 20 years old, but there were about 15% vessels which were 6 years and younger, and they were also lost. There was no question of any cyclone somewhere, there was no question of any grounding. The sea was deep, and in a very so-called undisturbed condition of the sea, the vessels were simply lost. Some of the vessels, they could get the wrecks. In some of the cases, they could get some surviving crew member. In majority of the cases, they could not even trace a single soul of the vessel itself, because they went so deep that they didn't know where it is. So whatever wrecks they got and whatever verdict they heard from those surviving crew members, they tried to analyze and came to a conclusion that the bulkers, if you just see the cross section of the bulk carrier, drawing the half of it, you have the upper wing tank here, and you have the wing tank like this here. Okay. You are having the frame here, which was being connected to some sort of a bracket down here and some sort of a bracket up here. Okay. Now the majority of the vessels, they found that the crack started from here, and this crack and the bracket which started progressively propagated to the stiffener here, and then finally to the hull, and opening it to the sea, and therefore from this side the water entered and slowly it flooded this part. It's basically a combination of many aspects. They found that why this has not, if it is fatigue here, fatigue could have been here also, but why it always on the bottom knee or knee bracket, why not in the top bracket? The thing is that when you are carrying any solid material in a loose condition, this corner cannot be cleaned properly, whereas it doesn't stick here, but it can stick here into some sort of a joints or knuckles there. The area is dark, and therefore if the inspector or surveyor, whoever goes there, he can't see it properly and can't make out whether the thing is properly cleaned, or even for the structural aspect, the welding aspect, he can't find it out. So if the cleaning is not done properly, the same is the case with the painting also. And with all those materials which goes and sticks there, either it is husk, or it is some chemical, or it is some dust particle, whatever you call it, they are prone to absorb moisture, and along with the moisture, oxygen. So they are rich in oxygen and moisture, and a lot of corrosion takes place. The effect of the corrosion is a smooth surface like this becomes a surface like this. Now if you see the surface top, each dent here is nothing but a pit hole here, and when this thing is subjected to some bending, there is a tension here, and tension means at this part the stress is going to 3 times the surface stress there. It is a small circular hole onto the surface, and on the surface whatever is the fiber stress, you can expect that on this side it is 3 times of that. And if that is the stress value, you are likely to have a failure here, a hair crack or hairline crack. But the thing is going in a cyclic manner, and therefore you are actually not seeing this, and because of the loading unloading, the material and dust will occupy this part. With the presence of the moisture, some sort of moisture means air is full, basically nitrogen, 78% nitrogen. So some sort of a metal nitrites and nitrates are formed here. These salt crystals try to cover up the crack, and it is sealed. So once the cracks are sealed, it again becomes smooth, intact. And when again the flexing takes place and it goes beyond that cracking stress of the salt crystal breaks and the metal surface freshly open to the atmosphere once again. It reacts. First it propagates, the crack propagates, then it reacts, and again it gets sealed, and this process goes on. So even if you try to check it, the surveyor will not be in a position to notice this with his naked eye, just because of the shear location, the lighting condition, and the phenomena which is occurring here. These are all the shipping classification societies consortium has done a combined research and come to a conclusion like this. But a stage comes when this keeps on propagating, and once again when it opens, you will find that the surface, if I just try to elaborate it here, say the crack has opened this much. That means this surface, this cross section is still intact to take the load. After that, when again it opens up, then the cross section, remaining cross section is less, but still it is capable of sustaining the load. And after that, when it cracks, you find that this is not in a position to take the further load. The stress goes beyond its capacity and the whole thing cracks. And this from here to here becomes a catastrophic crack. If you would have known that some crack is there, maybe some crack arrestor could have been done and repaired it. But it goes unnoticed in a progressive manner like this. Once people say, a massive heart attack is always associated with previous at least 2 mild heart attacks. So you can also say that here also some heart attacks are there. And then finally a massive breakdown takes place, and in such cases it simply goes beyond the hull and water rushes in. Okay, so though the thing seems to be very small and very insignificant, but the disaster level is very high here.
There must be hundreds of these, depending on how vast the corrosion level.
That is why people say that corrosion is to be taken care of. And corrosion is given a lot of importance, the material properties and the associated alloying elements which will prevent all this operation. And that is why the surface preparation, a proper painting, a proper survey after every 4 years, etc., is really a very important part in this case, as far as the health monitoring of the hull is concerned. And that is why people say that a good quality paint is to be used, because the surface is always under tension and compression. The type of paint, protective layer which we want, must have more or less the same mechanical properties as the surface of this material possesses. So if you are taking this is the surface, and on this you are putting a surface coat here, So, the interface must be intact all the time. Okay. When you are trying to flex this, either tension or compression, the two must expand or contract together. If suppose the expansion coefficient of this is less than this, or the elasticity, then there will be a crack developed here, and the corrosion will start from that, and pitting will take place. Okay. So, though this is a chapter of corrosion here, but still one finds that this theory can be applied on the surface cracks. Okay. That is what I was telling you, that I have not gone into the mathematics of it, but this what actually happens, and that is why one has to think about that, how to arrest these stresses or bring it to a level which can be maintained.
So R is any arbitrary value?
R. R is the location where you are trying to measure the stress, not arbitrary. Now, how do you find that how much of stresses are there? In ships, normally we do not try to measure these, but these days people are trying to measure it. But how actually you will come to know? If you have already taken the corrective measures like doubler plate and diamond plate at that region, obviously the stress level reduces there. But actually, how will you try to find out? Suppose you do not want to do all this mathematical analysis, but you would like to know that what I have talked so far, is there any sense, or I am just simply saying that it goes up to 3 sigma and you believe it? In fact, one thing can be added to this part here. When you are taking out material from here, okay, or let us come to this joint here. How do we take it out? We burn it out basically. Okay. So, with oxyacetylene gas you try to heat it, and then high pressure oxygen you blow it off, and therefore you get a neat cut here. So, you are heating it to the melting point, and then you are removing the material with high pressure air, and then you allow it to cool on its own. So, to remove the material we are heating and cooling. Are we controlling the rate of heating and rate of cooling? Not exactly. And therefore, in the vicinity of this, the property of the material or the crystalline structure of the matter or the material undergoes some changes, some metallurgical changes takes place because of the heating and cooling, and this part is known as heat affected zone, HAZ. Okay. After that we try to put some sort of either a doubler and then some sort of a combing. So, when you put a doubler here, you are again heating and cooling, right, and then when you are trying to put the thing, again you are heating and cooling, you are putting a combing here. Not only that, you will try to weld it from this side, you will try to weld it from the underneath also. So, basically at the same place you are trying to heat at least 4 times and cool it 4 times. And I do not know that whether any cooling rate or heating rate thing was properly controlled or not. Even if it is controlled, what is the effect of it? So, one has worked over this HAZ multiple times. When you heat, the material expands, when you cool, it gets contracted. Depending on the rate of heating and cooling, how much it expands and at what rate it contracts, there will be some strains developed here, and associated with the strains there will be some sort of a stresses which will be developed in this zone. So, heat affected zone is not free from stresses. And these stresses we say locked in stresses. So, these stresses are present, and on top of that stress now we are talking about this stress. So, we do not know the nature of this stress. If suppose we are talking about tension here and already some tensile stress is locked in, they will be additive here. Okay. So, if we are talking about 3 times this nominal stress here and some stress is already locked in practice it has been found that though theoretically we get a figure of 3 times the stress, but in practice sometimes you obtain 4.5 times the stresses as the peak value. Okay. So, the stress concentration when we talk about it is 3 to say 4.5 times. I would say that this is less, but it is never less than this. This is the lower limit, it can be anything in between, maybe 3.5, nearly 4. Okay. And therefore, this cannot be taken as very lightly. So, wherever one has any sort of opening, whether it is for the water intake or water exhaust, air intake, air exhaust, or it is for the hose pipe, anchor chain hose or whatever it is, or chain anchor pocket, everywhere you are having some sort of a opening, a manhole, a lightning hole, a hatch opening, whatever it is. So, they have to be strengthened. Number one, they have to be smoothened, and smoothing is done by giving avoiding all sharp corners, giving a rounding up. Even after cutting with the gas, one may try to polish it with a grinder, and then you strengthen it with the hatch combing. And care must be taken that as far as possible a good welding procedure should be used, so that in the heat affected zone the locked in stresses are removed, or try to see that there is very little locked in stresses. This what is very important here. Okay. Now, when we talked about this, then one would like to verify also. The easiest way of verifying it, that wherever you expect that there are stress concentration, try to measure the strain. Strain measurement can be done in full scale experiment. Which can be easily done by applying some strain gauges. Mostly they are electrical strain gauges, and applying those electrical strain gauges. There are different types of strain gauges available, unidirectional or multidirectional. One can choose it, apply the strain gauges, and then you can see that how the strains are varying at various locations, and one can have an idea. Okay. Another one is a mechanical observation, just the qualitative arrangement, where you expect, say for example, when we are talking about this hatch part, and this region you try to put some sort of a paint material, a brittle coating. So, when there is a stress concentration, the brittle material will have a crack, and knowing the amount of crack in a particular zone, one can find out that how much of stress is concentrated here. If you have number of cracks, large number of cracks in this zone, then you can say that the stress is concentrated. If some cracks are there, it may be continuous crack also, who knows. So then you can say that the stresses are less in this region, more in this region. But this will only give you a qualitative arrangement. This gives you a quantitative thing, but both are in a practical full-scale test, and full-scale tests are not easy to conduct because you won't like to take a risk that how this behave, and therefore you will always take a precautionary measure. Okay. Third one is that you have some sort of a scaled model. And conduct photoelastic test. In this case, the model must be transparent. And when we talk about transparent material, obviously it is not the parent material. There is a change in material. Okay. So you have to have a photoelastic material in which you can conduct the photoelastic measurements. You will try to get the material which is isotropic, but it will not have the similar mechanical properties as that of steel. So once again you will only try to get the nature of the stress concentration and the behavior, how it, what type of structure you are taking and how you expect the stresses will follow. Now the best way is you try to simulate that numerically. So you have done this model experiment, try to have a numerical simulation. And try to see that what type of stresses you get in your numerical simulation. Find out a correlation between this and this experiment. So if there is a 1:1 representation here, then you can say that your numerical simulation model will work for any size, any material. Okay? And from here you can predict in the actual case that how the stresses will vary. That is the latest, and that is why everywhere you go for a numerical simulation, and here the best way so far is the finite element method. Okay. So this what experimentally one will try to verify and then try to confirm that a particular numerical simulation method, a numerical method will try to predict that how the stresses will behave under such circumstances. So you can do a theoretical study knowing that one can take a preventive measure at the design stage itself. Okay. Any questions here? The stress concentration, I wanted to only cover this much, and all these experiments can be conducted because there are various shapes which are available now to be used in ships, like the circular hole is one. Then you may go for some sort of an elliptical hole also, like in lightning holes we use. Exactly it is not this thing, what we use is something like this. For this and this you have the mathematical expression, but from here one can extend it to this also. Then in the tankers etc., you have a hole like this. a cutout. Basically, if you see the bottom plate and you say that you have put a stiffener here, then actually this is not the shape you will get from here. The opening shape is something like this. Okay, this is welded here, and if they want to make it watertight, then they will put another plate sort of a thing here and try to cover it up and weld completely. Now this is one shape. If you are having a T-shape stiffener here, then what type of opening you will have? See, angle you can have a both sides you will be having. Now in that case, you know what they do. Many a times you like that the liquid should pass through one point to another point. Okay. So wherever it is a watertight floor, you try to seal it. Where it is not watertight hole, so instead of lightning hole, you combine the lightning hole with this cutout, and one can go for a hole like that. Okay. A very peculiar hole. Now this part basically, if you try to see, is nothing but this part, and this girder, and this is the part which is nothing but this part. Okay. If it is not like this, then one can go for this type of an opening. And then they will have a collar plate welded here. But this type of an opening will create a problem. You see what happens, you take the bottom, you weld this, and then you will take the floor and try to put it on top of it. So this part should be all clear, and therefore this goes well. Whereas this part will create a problem. Okay, you have to, yes, you have to take one by one and then put it in position and then try to weld it. That becomes a difficult part.
You cannot put it directly, you have to slide it along.
You have to slide it along the length. So that is why they have gone for this. If you open Lloyd's Register of Shipping's structural book, you will find this opening, you will find this opening. Now you see what is the complicated shape here. These are practically required, and theoretical result is available only for these two, a circular hole and elliptical hole. Even for a rectangular hole with circular ends, which we use as manholes, is not available. Okay, but one can extend this to this and try to use it. What about this part, which is a simple type of stiffener? Either you can have this for a angle iron, or you can have a slightly smaller one for a bulk plate. coefficients and change the units. See, when a particular person is trying to use the formula, it should be easy to use also, and therefore they found that what these two scientists come engineers have suggested is actually easy to use. Let us pass on to now composite construction. See, this term in shipbuilding started long back, when passenger crafts or the passenger ships were very much in use. Air traffic was very expensive, and I suppose transatlantic air traffic was not there at all. At that time, people used to move around the globe on ships only. The fact was known that the center of gravity of the ship plays an important role in the stability of the vessel, and the reputation of a passenger ship used to fall if the vessel used to severely roll and pitch, and that was only likely when the center of gravity is going high up. Two things: if it is too high up, so I can say that total force is equal to P aluminium plus P steel. What is P aluminium? No, sigma in aluminium into area of aluminium, and sigma in steel, area in steel. What is sigma aluminium? Now let me substitute from here. Sigma s let me take out, okay. So now whatever is here, this is equal to what? I say this is some sort of a sigma equivalent of steel, okay, which is equal to P now. Right? Sorry, not sigma equal, area equivalent steel. Now, what is this area equivalent steel? Area equivalent steel is area of steel plus area of aluminium converted to steel with this ratio. So, now this gives me a clue that in the bending case, whatever aluminium part is here, you convert this aluminium area to equivalent steel area this is O under 1. Okay. So, these materials are available in specification. We say that 300 grams per meter square or 450 grams per meter square. These are standard values available in the market. One can also get, say, I suppose 100 grams per meter square, 150 grams per meter square. Okay. So, you can get these materials in rolls. If you take 1 meter square, it will weigh so many grams. So, how much a glass content is there in that? Now, when you try to make a sheet, you have seen the helmets, they have these glass fibers in it. So, when you make a sheet, you take a particular volume of that, and in that volume how much of glass fibers are there, that tells us that what is the volume fraction of this. Usually we will find that the volume fraction of glass, that is the fiber we say, noted like this, is of the order of say 0.3, and it can go up to maximum 0.5. And volume fraction of resin, either resin or matrix they say, is sometimes we say that volume fraction of vacuum. When you try to mold the thing, some bubbles are there. It occupies the volume, it is embedded inside, but it does not provide any weight or it does not provide any strength. So, if something is there, then we can say that volume fraction of resin is equal to 1 minus Vf minus volume fraction of vacuum. Okay? Usually the construction method should be such that volume fraction of the vacuum should be equal to 0. We will do one thing, we will continue this in the next class. A little, I will not talk much about it, I will simply try to tell you about the materials.